Alrighty, we're gonna implement Conway's game of life in Ruby. And Conway's game of life is a zero-person game. It represents a grid of cells, and each cell can occupy one of two states, alive or dead, and then depending on the state of its neighbors, different things will happen to it. So it might die or it might stay alive, or if it's dead, it might come alive. So we're gonna start by creating a class called game of life. Define a constructor. And inside the constructor, we're just going to set up the grid that the game takes place on. And then looking at the problem statement, looks like we're going to need a transition function. And I think we'll also need a render function. So right off the bat, we can do a little bit more setup. GOL equals gameoflife.new, and then we'll just start with gol.render. So because it's a grid and it's cells that can have multiple states, I'm going to represent the grid as an array and each row in the grid as a string. And in Ruby, there's a shortcut way to do that. You can use this %w, and that will mean that anything delimited by a white space character is its own element of the array. So we'll do a 20 by 20 grid. That's 20. And then 1, 5, 6, 7, 8, 9, 10. That's 20 by 20. And then for the render, we're just going to do grid.each row, puts row, and then we'll run that in our terminal and see what kind of effect that has. That seems to be okay, but it could be nicer. We can add a space in between each element there, so we'll split on every character. That's what this empty string there represents, and that'll give us an array, and then that will join back together with a space in between each character. So then in here, when we run it, we'll get a nicer representation that looks a bit more square. So that's perfect, exactly what we want. Then going back to the problem statement, let's see here. Transition function is going to basically be recreating the grid. So we're going to say grid equals, and then we'll work through the grid one element at a time. And we're going to do that by going grid.each, except we're going to do each with index because we want to know the position of the element there as well as the value of it. And since we're going to be just collecting it back into the same kind of data structure, we'll call map, do row x, and then row.each char this time. And that's because it's a string, and this is a way to get an iterator, or I guess an enumerator, on the, I guess Ruby actually calls it an enumerable for each character of the string. So then we'll fill out the rest of it the same way as above. So now we'll get the cell and the y coordinate. So looking at these rules here, we can see that what all four of these rules have in common is that they're based off of the number of alive neighbors. So we're going to create a new method on this class. We'll mark it private, then we'll call it count alive neighbors. And we'll fill out the implementation for that in a little bit. So we'll just assume that works. So n equals count alive neighbors x, y. And then based off of the alive neighbors, there's a little bit of logic that we'll implement. So the first rule, any alive cell, so if a cell is alive, And here I'm using dashes to represent dead cells, and I'll use a pound symbol to represent an alive cell. So if cell is alive and it has fewer than 2 neighbors, then we'll return a dead cell. Else if, going on to the second rule here, if cell is alive and it has 2 or 3 neighbors, then it survives, stays alive. Then going on to the third rule, we have an alive cell with greater than 3 neighbors dies. And finally, if a dead cell has exactly 3 neighbors, then it becomes alive. And then we're going to do a catch-all kind of thing, an else to this if block. If none of the rules apply, then the cell just stays as is. And so this is complaining here because of using double quotes. That's just a weird editor preset. You should always use double quotes in Ruby. So that completes the logic for the rules of the game. Now we just need to figure out how to count the alive neighbors. And if we go into our terminal here, we can see that for a given cell, it'll have 3 neighbors here, 1 here, 3 here, 1 here. So a total of 8 neighbors. And we can apply the same logic for getting them on the edges too. We'll just have to filter out the coordinates that do not actually exist on the grid. So we'll construct an array of neighbors by using those coordinates. So like looking at this cell, this is xy, so this is x minus 1, y minus 1. So we'll start with x minus 1, y minus 1, then we'll go to x minus 1, y, and then x minus 1, y plus 1. So hopefully that makes sense as I type it out. X minus 1, y, x minus 1, y plus 1. So that's the 3 that are right here. Now we'll do this one and this one. So this should be x, y minus 1, and this one is x, y plus 1. X, y minus 1, x, y plus 1. And then the 3 on the other side. So those are going to match the 3 first ones, except it's going to be x plus 1 instead of x minus 1. So that's all the neighbors. But like I said before, if it's looking for the neighbors of a cell that's on the edge, we want to do some checks to make sure that we're not counting cells that don't exist. So we're going to do that while we count the number of neighbors that are alive. So we're going to go neighbors.map, C for coordinates, and if C0 is negative, or C1 is negative, then we're going to return 0. So we're just going to say next 0. Since this is a map, it's going to collect an array of zeros for dead neighbors, representing dead neighbors, and 1s representing alive neighbors. And then we'll sum it all up at the end to get the total number of alive neighbors. So this takes care of the case where they're going off the edge here and on the left-hand side. And now we'll do next 0, same thing for the other side. If C0 is greater than grid, the size of the grid, so the number of rows, -1 since it's 0 indexed, or C1 is greater than the size of the rows, also -1 because it's 0 indexed. So that takes care of those edge cases. Now we can get the cell from the grid, and that's going to be at C0, C1. And finally, if the cell is, we're going to use a ternary operator here. If the cell is alive, we're returning a 1, otherwise we're returning a 0. So a ternary operator is just like an inline if. So this is like, this is kind of saying if this, then this, else this. So that'll give us the total number of alive neighbors. So now we can kind of take a look at that. So we'll call gol.transition, and we'll just put in a puts, just so that there's a separator, and then we'll do gol.render again. So right now when we run this, hopefully we don't get any errors, but it's okay if we do. And the reason we got that error is that when we called map here, since it's not an array of arrays, it's an array of strings, we need to call dot join. So now when we run it, we can see that we got the first state and the second state, and they're identical, and that is because when there's no alive cells, nothing interesting will happen. So we'll put in some alive cells in a couple places. Let's see here. And just clean up this data a little bit and see what happens then. So we have our first state here with these lines, and then here we can see that since, for example, this cell has 3 alive neighbors, it spawned similarly to all of these. So basically the rules took effect. And we can see that this cell, for example, because it had 1, 2, 3, 4, or sorry, yeah, this cell has 1, 2, 3, 4 neighbors. That's not true. It has 1, 2, 3 neighbors. So I'm confused about which cell that is. I think that cell is starting off alive, maybe 1, 2, 3, 4, 5th. 1, 2, 3, 4, 5th. Yeah, so this cell is starting off alive here. That's this cell. But then because it has, it looks like it dies because it has greater than 3 neighbors, or maybe it has less than 2 neighbors. Let's see. 1, yeah, it only has 1 neighbor, 1 alive neighbor. That's why it dies. That makes sense. So let's render that a couple more times, and then to do that, we'll actually define a, we'll call it iterate method, and we'll say that it'll iterate 10 times by default. And so we'll do n.times do, and then we will say render transition, and it's highlighting render as if it's a keyword. That's very interesting. And then we'll sleep for 1/4 of a second. So it'll be 4 frames per second this way. And in order to kind of clear this screen, we can use a special character sequence that kind of encodes a command to really set the terminal. Then this, I think this only works in like a Unix-based system. So we'll say gol.iterate and kind of take a look at what that produces. So that was pretty cool. Let's see if we can iterate 30 times just to see if it reaches kind of a stable point where it's no longer changing. And it doesn't look like it does in 30 frames. But anyway, that's Conway's Game of Life. Hopefully this is a useful overview. Yeah, that's about it.